Hi everyone, in this video we're going to go through section 6.2 titled Orthogonal Sets. So we were introduced to the term orthogonal in the previous section, and now we look at sets that are made up of vectors that are orthogonal to each other. And we define an orthogonal subset of Rn first. It's a set of vectors. Often we're using U's here in this for orthogonal vectors, and it's said to be an orthogonal set if each pair of distinct vectors in the set is orthogonal. That is, their dot product is equal to 0 for each pair of vectors in the set. Now, if you consider the elementary basis, I hat, j hat, and k hat, right? I hat's entries are 1, 0, 0. J hat's entries are 0, 1, 0. And k hat's entries are 0, 0, 1. If you take the dot product of any pair of those three vectors, they will in fact be orthogonal to each other, so that set of vectors is an orthogonal set. Here we have a set of vectors where the dot product is not immediately as obvious for each pair, but we still have to check each one to show that the set is itself orthogonal. So we take u1 dot u2, and I'll write this out. That's -3, add 2, add 1, which is 0. Then we take u1 dot u3, and for that one you get, let's see, -3 halves minus 2, add 7 halves when you do that multiplication. And let's see, -3 halves add 7 halves is 4 halves, which is 2, minus 2 is 0. And then u2 dot u3, let's see, we get +1/2, we get -4, and +7 halves when you do that product. 7 halves add a half is 8 halves, which is 4 minus 4 is 0. There we go. So we have 3 dot products to verify that set is orthogonal. So that's an orthogonal set. Now we get to the theorem in the section. Theorem 4 says that if I have a set of vectors that are orthogonal to each other, so an orthogonal set, then S is also linearly independent and hence a basis for the subspace spanned by that set. Okay, so it says if I know my vectors are orthogonal, if it's an orthogonal set, then that set is linearly independent and a basis for the subspace spanned by S. Okay, so this is one that we are going to go through a proof of because it's kind of cool how it works out. Okay, so I'll write proof there. And the way that we prove this, we need to show that it's linearly independent. So we write a linear combination, 0 equals C1 U1 plus ... CP UP for scalars C1 through CP. Okay, so we take that linear combination. Oh, actually, let me add the word if at the beginning. If that linear combination equals 0, what we need to show is it has only the trivial solution. Right? If it only has the trivial solution, then the set is linearly independent. If that is true, if that linear combination equals 0, then I can take and write a dot product, and you'll see which one I write down. I'm going to say 0 is equal to 0 dot u1. So I'm going to take that u1 vector, the dot product of it, and the left-hand side is 0. That should make sense. And I'm going to take the dot product on the right-hand side also. C1 u1 plus C, I'm going to write C2 also, even though I didn't in the previous step, plus CP UP, all of that, dot u1. Okay, so we take that dot product there. And now, property of the dot product is that I can distribute that over the sum. So 0 is equal to C1 U1 dot U1. And these guys technically are grouped here, but I'm going to change that in the next step. Plus C2 U2 dot U1 plus etc. Oh, and I forgot my dots up there in the previous step. There. Plus CP UP dot U1. Okay, so we take that dot product, distribute the U1 vector into the parentheses, and now in my next step, all I'm going to do is regroup things, right? I can take the scalar and multiply first, that's the property, or I can take the dot product and compute that first. Okay, so this is C1 times U1 dot U1 plus C2 times U2 dot U2, etc. Oops. CP UP. Hang on. P dot U1. There we go. And I just noticed an error. That should be a U1 vector right there. I'm distributing the U1 into the parentheses. Okay, now here we get to the cool part. So in this linear combination, what I'm going to underline in red is equal to 0 and everything in between. Okay, think for a second why that has to be 0. I'll tell you the answer shortly, or I'll underline it. If that set is orthogonal, this dot product equals 0, this dot product equals 0, and every dot product in between is equal to 0, leaving only 0 equals C1 times U1 dot, oops, not plus, dot U1. Cool. So everything else dropped out because I took that dot product. Now, we're almost at the end of the proof. Next thing I'm going to say is, let's move this up a little bit here. Next thing I'm going to say is because U1 is, the reason for that. Yeah, I'm actually showing my work here. Because U1 is, that is true because U1 is orthogonal to every other vector in the set. U2 through UP. That's why all of that canceled out, basically. Now, since U1 is not the 0 vector, since it's not equal to 0, it's the dot product of U1 and itself cannot be 0. It must be positive. So C1, the only option, is for C1 to be 0. Now, that's technically not the end of the proof, but what we can do is we can say a similar argument shows that C2 through CP must also be 0. Must also be 0. C2 would be 0 if I took the dot product with U2 and distributed it through. C3 would be 0 if I took the dot product with U3 and distributed it through. Okay, so that's kind of the part of the proof that we don't have to write down because it'd be the same thing over and over. Okay, so those must also all be 0. Oh, yeah, so thus, or therefore, S is linearly independent. It is a linearly independent set. Cool. All right, and so the question then becomes, what's the significance of an orthogonal basis? They just play nicer than other bases. They're easier to work with. They have more useful properties. So if I know the vectors are orthogonal, it's a nicer basis to work with, basically. All right, the top of the slide has a pretty bland definition. Defining an orthogonal basis, it's just a basis that is also an orthogonal set. Nothing hugely significant there. Theorem 5, I'm not going to do a proof of. I will point at things and talk about them. But if I have an orthogonal basis of a subspace, then for each vector, each y in W, each vector in that subspace, the weights in the linear combination y equals C1, U1, etc., so the weights in that linear combination, so how I form y out of the basis vectors, those weights can all be found using a formula. Cj, so the jth weight is y dot uj over j dot uj for each vector in the set, for each scalar in the set. So you can find them using a formula. And where that comes from, the same way in the proof on the previous slide, if I take that in parentheses, dot u1, and then y dot u1, the same thing happens, and you can write it out. I think they may even go into more detail in the book, but you can certainly write that down and figure it out, how you go from the linear combination at the top to this formula at the bottom. And this is the nice thing about an orthogonal basis, is that it allows us to write formulas for some things where we don't necessarily have them. Now, in example 2, we use the formula that we were just given on the previous slide, and we have our orthogonal basis from example 1, and we need to write y as a linear combination of the vectors in S, and we're going to do that using the formula. Okay, so what we need is a few different dot products to find each scalar. So what we'll do on the right here is we're going to take y dot u1 and u1 dot u1. First, compute those two dot products. So my y vector dot u1. 6 times 3 is 18, plus 1 is 19, minus 8 is 11. And then we take u1 dot itself, you also get 11. Okay, I'm going to go through the other dot products a little bit more quickly. The next one is y dot u2, u2 dot u2, negative 12, 6. Y dot u3, u3 dot u3, and that is negative 33 and 33 halves. So that one is a little bit ugly right there. All right, so that's the work on the dot product. Now each weight from the definition, or from the previous theorem, each weight is this over this, this over this, this over this. Okay, so that was the formula. The weight, the Cj, is equal to y dot j over uj dot uj. Right? So take each of those three ratios, and we can write y as a linear combination of u1, u2, and u3. So u1, his coefficient is 1. u2, his coefficient is negative 2, right? Negative 12 over 6. And u3, his coefficient is also negative 2, negative 2 u3. That ratio, it simplifies to just negative 2. All right, so that's the cool thing about an orthogonal basis, is I can solve and find those weights. Or, right, we've been at this for a while now, so we're remembering things from earlier in the course, or just do chapter 1 stuff. Do chapter 1 stuff, right? I can take and do some row operations. 3, 1, 1, minus 1, 2, 1, negative a half, negative 2, 7 halves, 6, 1, negative 8, put it into reduced row echelon form, boom, you got your weights. But because it's orthogonal, I don't need to do that. I can just use this cool relationship that is present in orthogonal bases. The next topic in this section is something called an orthogonal projection. And what an orthogonal projection is our goal is kind of to take a vector, let me write this goal, is to take a vector y and write it, decompose it, break it apart into two different vectors, but two really specific vectors. And we're going to name them y hat and z. And the relationship, what we're splitting y up into, the two different vectors, one of them happens to be a multiple of some vector u in a subspace, and I'll show you what that looks like in just a second. I want to just kind of go through the setup here. One of them is a multiple of a vector in a subspace, and the other one is orthogonal to that vector. Okay, so let me take this away, and I'll show you what I'm talking about here at this expertly drawn image. Okay, so I have my subspace W. Right, I got a subspace W. Let me get my pointer there. Let's use this one. All right, so we have our blue subspace W. We got U and W that's just pointing over here, right? He's right on the subspace. And then here's my vector Y. This guy is my vector Y. That's the one that we're decomposing, breaking up into two different vectors, okay? One of those vectors lies on the subspace and is just a scalar of U. And the other one, Z, is orthogonal to U. These two vectors are orthogonal to each other over here. They're also orthogonal over here. Okay, and if I add there we go. If I add y hat plus z, I get the vector y, tip-to-tail addition. That's how addition works, right? So that's kind of the image that we're looking at. You may have seen this topic previously if you took Calc 3. I'm pretty sure it was called orthogonal projection. If you take and shine, let me use yellow because I'm talking about a light. If you take and shine a light down at the vector y, its shadow falls down on that plane, right? And if I look at its shadow pointing in some specific direction, specific direction u, right, the shadow would be cast down here, and that would be a 90-degree right angle right there. Okay, so if you've taken Calc 3, you may have seen this in a little bit in that course. Okay, but if not, here's your introduction to it. Ultimately, that's what we're doing. We're decomposing y into a sum of really specific vectors. Now, move this box over here, and we get our formula for it, which should look familiar. Okay, y is the orthogonal, y hat, excuse me, that's what we have a formula for. Y hat, that's the orthogonal projection of y onto our subspace W, right? So that's a subscript of W and a regular script Y. So the orthogonal projection of Y onto W is what we call y hat, and it's y dot u over u dot u times u. And u is just the direction that we're pointing on the subspace. Okay, now in example 3, we're going to find an orthogonal projection. We're given our y, we're given u, and we want to find that orthogonal projection of y onto, not a subspace W, but onto the vector u. Okay, do it the same way as the previous slide. We take y dot u and u dot u. Y dot u, that dot product is equal to, let's see, 7 times 4 is 28, plus 12 is 40. And u dot u, that is 16 plus 4 is 20. And so then our y hat is 40 divided by 20 times the vector u times 4, 2. And when you simplify that, you get, let's see, the vector 8, 4. And I didn't write it, but let me write it over here. That is the projection, the orthogonal projection of y onto the vector u. I'm going to kind of sketch this out so we can take a look at what's going on here. Let me draw a little scale here. 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, approximately. And our first vector y is 7, 6. Oops, I got to go a little higher on the y. 5, 6. Our first vector y is 7, 6. That's up here approximately. There's my y. And then my vector, let's see, let me draw a line to it. Pretty good. And then my vector u is 4, 2. Change colors here. 4, 2. This is the vector u. And then let's change colors a third time. We'll go black this time. And 8, 4 is right about there, approximately. Now, 8, 4 should be on the same line as u. That's y hat. And now I'm obviously not drawing on graph paper here, but this should be a 90-degree right angle. Okay, that's, if I were on graph paper, it would look much better, but I'm not. Okay, so there is our y hat, the orthogonal projection. We have one other thing to find, that is the z vector. The z vector is that little black vector that I drew in there. To find that, since it's y equals y hat plus z, well, z would equal y minus y hat. So in this case, it is 7, 6 minus 8, 4. And that simplifies to -1, 2. And you can kind of look, it's -1 in the x direction and 2 in the y direction. The rise over the run, that's 2 units, that's 1 unit, and it's a downward slope. Okay, this is my x direction, this is my y direction. All right, so that's all we had to do for that one. Okay, in example 4, they refer to L. If you didn't know, there was something in the text that didn't get added into the notes. L is just the span of the vector u. So it's just all the points on that line are referred to as L. So the distance from the vector y to the line L is that that perpendicular. It's the length. How do I want to write this? The distance from y to L is the length of the perpendicular line segment from y to y hat. Line segment y to y hat. Okay, that's the z vector, or we can just write it as y minus y hat. And that length is the square root of 5. 1 plus 4 is 5, the square root. and that represents the shortest distance from the tip of that vector, y, to any point on line L. Our text very briefly talks about an application to this concept in terms of decomposing a force into component forces. We don't get into any examples or anything, but that's just one area where this topic applies. We get a definition here on this next slide, and that is for an orthonormal set. Notice it's not orthogonal, it's orthonormal. Okay, we throw the word normal on, and that means that each vector in the set has to be a unit vector, meaning they have a length of 1 unit. So like they're special because they're orthogonal, they're super duper special because they have a length of 1. Okay, so that's the new definition that we get in this on this slide. And we have an example where we have to show that something is an orthonormal basis. So we have a little bit of work to do here. We need to find, 4 different dot products: v1 dot v2, v1 dot v3, v2 dot v3. And when I said 4, I of course meant 3. All of those dot products should be equal to 0. Check them in your calculator if you want to, or do them in your brain if you're really smart. They are all equal to 0. Then the other step that we would have to do is to find the length of v1, the length of v2, and the length of v3, and show that those are all equal to 1. I'll do one of them, and then I'll just write 1s for the other 2. This first one, 3 over radical 11 squared plus 1 over radical 11 squared plus 1 over radical 11 squared. Square each of those entries. That's 9 over 11, 10 over 11, 11 over 11. I'm doing the addition as I go. The square root of 11 over 11 is equal to 1. The other 2, the same thing happens. So that set of vectors is an orthonormal basis. Also, the standard basis of R3 is orthonormal. Theorem 6 has a cool proof. It's in the book. I think you should read it. But in Theorem 6, we have a matrix U has orthonormal columns if and only if U transpose U is equal to the identity. So if the matrix has orthonormal columns, then this relationship is true. If we check 2 matrices and we establish this relationship, then we know that the columns have to be orthonormal. So you take the transpose times the original matrix, and you produce the identity. Again, the text has a pretty neat proof of it. You should give it a read. I won't test you on it or anything, of course, but it's a good one. Now we get to Theorem 7, where we have a matrix U that has orthonormal columns. X and Y are vectors in Rn. Then the length of U times X is equal to the length of X. That's kind of cool. If I multiply X by an orthonormal matrix, or a matrix with orthonormal columns, it doesn't change the vector X. Just kind of a cool property there. U times X dot U times Y is equal to X times Y. So even though I'm multiplying them both by U, I don't change the dot product at all. Did I say times? The dot product, X and Y. Ux dot Uy is equal to 0 if and only if the dot product of X and Y is equal to 0. So just a little theorem, some properties that we may encounter as we go through this section, the homework on this section. And finally, we get to an example where we verify a property from the previous theorem, and it's this one right there. So we have a matrix U, a matrix X. They tell us that U transpose U is equal to the identity that verifies that it is orthonormal. So if we take the length of U times X, that should equal the length of X. So that's what we have to find. And I'll do the length of X first. So that would be the square root of radical 2 squared plus 3 squared. 9 plus 2 is 11, root 11. There we go. And if I want to do the length of Ux, well, first I need to find that product. We'll do that up here since they're close to each other. So let's see, U times X is equal to, so I've got to go row to column. 1 over radical 2 times radical 2 is 1, plus 2/3 times 3. 1 plus 2 is 3 for that entry. And then 1 over radical 2 times radical 2, well, that's 1 again. And then minus 2 is negative 1. and then 0 times radical 2 plus a third times 3. I think that's going to be 1. So 3, negative 1, 1. And the length of that is 3 squared, negative 1 squared, 1 squared. And we get, let's see, well, 9, 10, 11, the square root of 11. Wow, that's kind of cool. So even though x only has 2 entries, u times x has 3 entries, they have the same length. That's kind of a cool property there. All right, and that's how we'll close out the section. Thank you for listening. I hope that kind of made sense. If it didn't make sense, then please let me know. Shoot me an email, send something on Blackboard, and I will do my best to address whatever confusing thing I may have said. Thank you for listening. Have a great day.